axis for this S section beam. So to do this, the first step we're going to do is we're going to split our beam into different areas. Alright, so we have our XY axis that goes through the centroid of our section. We have our section is shaped like an S. Alright, so we can break this section into 3 parts. We're going to break them into section 1, section 2, and section 3. So we want to determine what is the total moment about the x-axis and what is the total moment of inertia about the y-axis. So for the x-axis, we would say that the total moment of inertia would be equal to the moment of inertia about the x-axis for section 1 plus the moment of inertia about the x-axis of section 2 plus the moment of inertia about the x-axis for section 3. Very similarly, for the moment of inertia about the y-axis, it would be equal to the moment of inertia of section 1 plus the moment of inertia of section 2 about the y-axis plus the moment of inertia about section 3 for the y-axis. Right. So once you have those formulas defined and you split your cross-section into different areas, the next thing we're going to do is we're going to calculate, for each area, we're going to calculate I of x and I of y for each area. So for area 1, we're going to calculate Ix1. So we're going to use the parallel axis theorem. So we know that Ix1 about the centroid of area 1 plus the area of section 1 times the distance y squared. So we're going to just define each of these terms. So for a rectangle with a base, we know the moment of inertia of a rectangle about its centroid is equal to 1/12 times the base times the height cubed. You can look up this formula in the table in the packet that's a couple pages above here, so you can see in this table for a rectangle we have I of x is equal to 1/12 the base times the height cubed. Alright, so and then the area is just equal to the base times the height. Alright, and then the distance dy is just the distance from the x-axis to the centroid of our area. Alright, so if we plug in all of those terms, what we'll end up getting is our base of a rectangle is just equal to 100 millimeters. The height of our rectangle is equal to 400 millimeters minus 100 millimeters, or 300 millimeters cubed. So, alright, I'm just getting these from the diagram on the top left of the screen. Alright, and then the base again is going to be 100 millimeters times the height, which is going to be 300 millimeters. And then our d of y is going to be equal to 50 millimeters, which is the thickness of section 2, half of the thickness of section 2, and half of the height of section 1. So it's going to be 150 millimeters plus 50 millimeters, and that's going to be squared. Okay. So if we do all of that, what we end up getting for Ix1 is equal to 1425 times 10 to the 6th millimeters to the 4th. Right. So we can do the same process, but for y of 1, if we do that, you know it's equal, the equation is going to be the moment of inertia about the y-axis of the centroid plus a times dx squared. So y of 1 is equal to 1/12 the height times the base cubed plus the height times the base, or the area, times dx. Right, so if we plug in our known terms, you get 1/12 times the height, in this case is 300 millimeters, times the base, which is equal to just 100 millimeters, plus the height, so 300 millimeters times 100 millimeters times dx, which is going to be the distance from the y-axis to the center of section 1. So we know that that would be equal to 300 millimeters minus half of the thickness. So we know it's going to be equal to 250 millimeters. Alright. And that would be squared. Alright, so if we what we end up getting for IY1 is IY1 is going to be equal to 25 times 10 to the 6th millimeters to the 4th plus 1875 times 10 to the 6th millimeters to the 4th, which is just going to end up being 1900 millimeters to the 4th times 10 to the 6th millimeters to the 4th. Alright, so the one thing I will mention here is that area 3 has the same properties, or same shape really, as area 1. The only thing is that they're just that they have negative dy term, and they have a positive dx term. It's the only difference between the two sections. Alright, but since d of x and d of y are squared in the parallel axis formula, I1 of x will equal I3 of x, and I1 of y will equal I1 of I3 of y. So in short, the only thing we need to do now is we just need to calculate for area 2. So the area 2's moment of inertia about the x-axis is going to be equal to, it's a rectangle again, so it's just equal to 1/12 the base times the height cubed. So this is just Ix2 about the central axis plus the area times dy squared. So if we plug in our values here, we get 1/12 the base of our rectangle is going to be equal to 600 millimeters. I'm just getting that from the dimensions that were given to us in the problem statement, times the height, which is equal to 100 millimeters cubed. Alright, and then our area would be equal to 600 millimeters times 100 millimeters. Alright, but since the centroid of our shape is of our area and the centroid of the axis we're trying to find the moment of inertia about are the same, our d of y in this case is going to be equal to 0 millimeters. So this whole term will end up just being equal to 0, and we'll end up getting for Ix to the 12th, we'll end up Ix2 will end up with 50 times 10 to the 6th millimeters to the 4th. Right. And then we can do the same process for Iy2, where we would get it'd be equal to the moment of inertia about the centroid of our area. Alright, and then we'd get, so that would be equal to 1/12 the height times the base cubed, plus our area times d of x squared. So our area would just be equal to the height times the base, and then we'd have dx squared. Alright, so if we plug in all those terms, we end up with getting 1/12 times 100 millimeters cubed, 100 millimeters times 600 millimeters cubed, plus 100 millimeters times 600 millimeters times, again, the moment of inertia, or the centroid of area 2 is at the same point as is the global coordinate system, or the x and y axes. So because of that, our d of x term will also be equal to 0 millimeters squared. So again, our a dx term will be equal to 0, and we'll end up just getting, for Iy2, we end up getting 1800 times 10 to the 6th millimeters to the 4th. Alright, so the only thing we have left now is we have to just sum our moments together to find I of x total and I of y total. So if we do that, what we end up getting is we get I of x would be equal to 1425 times 10 to the 6th millimeters to the 4th, plus so this would be Ix1. Ix2 would be, we just saw was just equal to 50 times 10 to the 6th millimeters to the 4th, and then Ix3 is equal to Ix1, so it would be equal to 1425 times 10 to the 6th millimeters to the 4th. So we add this all together, we end up getting 2.90 times 10 to the 9th millimeters to the 4th. Alright, and we can do the same thing for I of y, where we would get, it'd be equal to I y of 1 plus I y of 2 plus I y of 3. So I y of 1 we solved for was equal to 1900 times 10 to the 6th millimeters to the 4th. Then I y of 2 would be equal to 1800 times 10 to the 6th millimeters to the 4th, and then Iy of 3 is equal to Iy of 1, so it would be equal to 1900 times 10 to the 6th millimeters to the 4th. If we add those all together, we'd end up getting 5600 times 10 to the 6 millimeters to the 4th, or 5.60 times 10 to the 9th millimeters to the 4th. Alright. So those are our two answers. So just to recap what we did in terms of steps. We first split our cross section into different areas. So in this case, we had three areas: area 1, area 2, and area 3. We would then use the parallel axis theorem to calculate Ix and Iy for each area. So we did that. We took advantage of the fact that area 3 and area 1 had the same properties, so they had the same values of dy and dx in terms of the magnitudes of those two. The areas were the same, and so that made it really simple to calculate. It reduced the number of calculations we had to make in this case to just 2, and then we calculated the moment of inertia for area 2. And then the last thing we did was just add all the moment of inertias together, right, to determine the total moments. Right. So that concludes this example problem on how to calculate the moment of inertia for a composite section about both the x and y axes.